All right, recording is rolling. Welcome to Monday, September 11th. Got an exciting day here. We'll start with top scientist for a linear motion quiz. So if you're on this list, you did really good on the quiz. Actually, I don't have my seventh period, so sorry if you're in my seventh period. I will get some names there. Just we didn't have a seventh period back on Friday because of the storm, right? But you guys turn those in. Okay. Some of you guys are really awesome. Right? If you're on this list, you did really good. So some of you guys really struggle with that. I know that was the very first physics quiz in here. Right? You guys are kind of getting used to how things are working, what kinds of questions could be thrown at you. So there's going to be a corrections opportunity. Eventually, I'm going to hand these quizzes back. I have to get them all in first, right? Including seeing my seventh period. And a couple of guys may have been absent last week too. Right? But once everybody's turned them in and I've got them all graded, then I'll give those back to you guys. I've like circled the right answers, or in the case of the graphs, like drawing the correct graph. So if you like write out, like hand write out on a separate piece of paper, like the steps to get to the correct answers, or in case of graphs, just like draw the graphs correctly and turn this back in, then I'll give you guys a partial credit back. Okay. So if you did real bad, then it won't be like as bad. Okay. Okay. Today, I'll take you guys through at least a couple of projectile motion questions on paper. We're going to solve these out. Today's the last day for projectile motion. I just want to do like one more day just for a little bit of extra practice and review. Come back from the weekend. Okay. And we're going to tomorrow we're going to move on to new stuff. We'll move on to forces, Newton's laws, dynamics. Okay. I do have a new quiz for you guys. I will get this quiz to you guys before you walk out of class today. So here's another take-home quiz. It'll be due on Friday, so Friday the 15th. Right? You guys good? All right. Then new stuff. Before I started the recording, I passed you guys out a couple of things. One thing I passed you guys out were some textbook puzzles. Right, so yeah, we'll go ahead and just go through textbook. I think these are good enough. They pretty well check the boxes this time. Okay. So your textbook organizes it chapter 4, forces in one dimension, and then chapter 5, forces in two dimensions. I picked a few problems from each one. Okay, so just the ones that I circled, I'll have you guys turn in. And my plan is to actually go over a lot of these with you guys in class. So as long as you're in class, just following along, should be able to knock out probably most of the ones I circled, I think. Okay, solidly. Okay. And so those won't be due for a few weeks. Let's have it 9/29. It's like the last day in class in September. Okay, so got a few weeks on those. Okay. A lot of fun stuff we'll have going to this class, a lot of labs. In the meantime, do more graphs, more provide diagrams, right? And then I'll do some of these with you guys in class. Okay. And then tomorrow I'll set you guys up with the spring scales lab involving a whole bunch of spring scales and lab weights. So near the end of class today, I'll take you guys in a little bit more on that. It's really going to be like 10 mini labs. And pay real close attention to what you're doing tomorrow, because I'm going to be referencing those 10 mini labs for many weeks to come. All right. So, yeah. So, you guys good with what we're doing so far? All right. Step here. Before I hit record, you guys are walking and have this challenge question up here. Well, it's a couple of questions. One that I think is pretty straightforward, and one that's a really good challenge question you have to think really deeply on. Okay. So, you guys had a couple minutes to look at this. So, man. Let's do it. Right. So zookeeper devises a rubber band gun to shoot food to a monkey who's too shy to come down from the trees. Oh yeah, look at that. Here's a zookeeper with a slingshot. He's got a banana, and he wants to fire the banana so that it gets to the monkey. Right. Now, first question I think all you guys are gonna get. Right. If the monkey does not move, then should the keeper aim above, at, or below the monkey? Let me see, show of hands. How many guys think that the zookeeper should aim above the monkey to get the banana to the monkey if he's stuck in the trees? What do you guys think about aim above the monkey? Yeah, you guys are right. You guys are right. Okay. Now, what angle? Well, that depends how fast he's blasting it, and also how far away horizontally and how far vertically up the tree is, right? So that could be something you could solve, right? Like what angle should he aim at? Pretty tough, but you could solve that. Right? Maybe he aims it kind of shallow above this dash line. This dash line is like a straight line distance, right? He aims a little shallow, like really fast, goes, or maybe he aims at like a pretty good angle above, but kind of lobs like, just kind of lobs towards the monkey, right? But you would have to aim above that dash line unless maybe you turn gravity off. Could you guys imagine just turn gravity off as a variable? In that case, where should he aim? Straight at the monkey, right? Straight at this along this dash line path, right at the monkey. That's if you turn gravity off. If you turn gravity back on, well, now gravity's always pulling down. You have to aim above the monkey. Okay, you guys get that. Now here's the real challenge question right here. If the monkey lets go of the branch at the instant the keeper shoots the banana, right? Let's say he knows it's going to play out that way. As soon as this guy lets go of the banana, the monkey's let go of the tree branch at the exact same time. In that case, should he have aimed above, out, or below the monkey so that the monkey can catch the banana in midair? That's another part of this. The monkey's going to catch the banana before he hits the ground. Okay, right, so to catch the banana in midair, where should that zookeeper have aimed? Okay. Show hands. How many guys think he should still aim above the monkey? Still aim above the monkey. Ooh, no one say that? Okay. Who thinks he should aim straight at the monkey? Straight at the monkey. Who says below the monkey? Below the monkey. Okay, I'm seeing most hands on below the monkey. I asked my AP class last hour or two. They said the same thing. I think that's like the intuitive answer, but that's actually not the correct answer. The correct answer is you should aim straight at the monkey. Okay? Now again, this is a pretty tough one to think about, but here's the solution here. Straight at the monkey. Now, why would it be straight at the monkey? Okay? Well, it has to do, think about how far the monkey has fallen in terms of time versus how far would the banana deviate from the straight line path as a function of time. And they end up being the same height change. The expression I can point to back that up would be this first one right here. Right? So how far would it fall or like deviate from the dash line as a function of time fall? Right? Now for the monkey, it's just very simply the height fall is 1/2 gt squared. Right? 1/2 gt squared. If he's been falling for 1 second, he fell 5 meters. Right? You guys get that, right? H is 1/2 gt squared. That's the college equation. College. Right? Now for the banana, remember if there's no gravity, it will just follow the straight line path. Right? Now if you turn gravity back on, it's going to fall into a parabola shape and it will deviate from the straight line path. Right? How much will it deviate from the straight line path? Well, the way I could modify this first kinematic equation, I could say instead of x, I could say y, like some height, some like vertical position I'm looking at. Right? Instead of v naught, like some general speed, I could say v naught in the y direction. Right? Okay, so its height would be y could be v naught y times the amount of time it's been flying for. Right? And I say minus 1/2 gt squared. And this minus 1/2 gt squared would represent the amount that the banana deviates from the straight dash line path. Right? And as long as the banana gets to the monkey before the monkey hits the ground, yeah, the zookeeper should have aimed straight at the monkey. Okay. That one's pretty fun. You know what? There's a couple other questions. Let's do the other 2D questions in here. Speed of an airplane relative to the ground is affected by wind. When the airplane flies in the direction of the wind, say it gets a tailwind, it has a greater ground speed, right? Because it's getting the boost. You can add the vector scale like that. When the airplane flies directly into the wind, a headwind has a smaller ground speed because now it's always fighting the air. Right? So if the plane's flying this way and the air is going this way, now the plane's going really slow compared to the ground, right? It's like fighting the wind. Okay, so we've got all that. That's all in one dimension. Right, now here's the kind of tricky question. What about when the airplane flies with a 90-degree crosswind? So the plane's flying north at 40 meters per second, and along comes a 30 meter per second crosswind. Okay? Now will the plane's ground speed be more or less the same as compared to no wind at all? Okay? So some guy on the ground with a radar gun is pointing straight up at the plane. Okay? Show of hands. How many guys think that with the crosswind, so 40 meters per second the plane's flying, got a 30 meter per second crosswind. How many guys think with the crosswind, the ground speed would be more than with no wind at all? Would be faster? Who says faster? Who says slower? And who says the same? Okay. If you said more than, maybe you remember, you guys saw this question last week, right? This was on the Kahoot. You guys remember this? This is one of those conceptual questions. Let me prove it to you guys. You guys here. So velocity vectors. Let's have the plane go on 40 meters per second. Now that's the plane relative to the surrounding air. So the propeller can only push so hard against the surrounding air. Right? The plane doesn't know anything about the ground. All the plane knows is about the environment that it's in, about the air that it's swimming in. Right? But let's have a 30 meter per second crosswind. Now there's the air relative to the ground. Notice I connected those vectors tip to tail. You guys see tip to tail, right? Because the plane's always kind of flying north, the wind's always kind of blowing east, right? So I connect this tip to tail. If I go from the tail of the first vector to the tip of the last vector, that vector right there is called the, what kind of vector starts with an R? Resultant. Resultant. Oh yeah, resultant. Okay. And does anybody know the magnitude of that resultant based on what I just drew? How fast is that? 50 meters per second. All right. How do you know it was 50 meters per second? Ah, the equation. Oh, Pythagorean. Yeah, go. 30 squared plus 40 squared, square root, units meters per second. Yeah, this Pythagorean theorem, right? I did set up a 3, 4, 5 proportion triangle. Not all triangles obviously that proportion. I like to use those a lot though. Okay. Yeah. All right, you guys good? All right, let's do one more out of this book. Here we go. Boy on a tower throws a ball 20 meters downrange, as shown. Ooh, got a 5 meter tall tower. Looks like he threw that ball straight horizontal and landed 20 meters from the base. Question, what is his pitching speed? What is his pitching speed? Raise your hand when you know the answer. When you know the answer, raise your hand. Up.
Can I give you
What you got?
it's like almost
Okay, oh yeah, you got that. That's the answer. That's what we're looking for. All right. 20 meters per second. How'd you know? How'd you know it's 20 meters per second?
because it was all 5 meters.
Boom. Exactly. Right. Yeah. Yeah. 5 meter drop height. Yeah. It takes a second to fall that far. Right. Or if you like, if you go to the edge of a cliff and you drop the ball and let it fall for a second, it will fall in 5 meters. Okay. Now, in this class, I've been saying 5 meters. You guys know gravity isn't exactly gravity field on Earth, not exactly 10 meters per second squared. It's like 9.8 meters per second squared. Okay. That's where they're pulling a 4.9 meter tower from. They're using a more exact version of gravity. Right. You guys see it? Right. Okay. Yeah. So exactly 1 second takes to fall. If this guy just dropped the ball, it would be hitting the ground in 1 second. If he throws any ball horizontally, it also hits the ground in 1 second because they have the same vertical motion. Okay, so it went 20 meters across in that 1 second of fall time. Oh, 20 meters per second, he was throwing the ball. It was always going across the field at 20 meters per second. Right? Guys good? All right. Let's do a couple of projectiles here. A couple of projectiles. There's different versions of the quiz that I'm about to get you guys in a few minutes. I just want to do this review first. Okay. So there's two main classifications of questions you might get in this review. I want to do one of each one. Okay. So if you're ready to build either of those. Okay. So let's start with something really similar to what you guys just saw. Let's put a cannon on a cliff, just aim it straight horizontal, and blast the cannonball straight horizontal. Boom. That's like almost exactly what you guys saw. Hit on the tower, goes the ball horizontal. The same thing, right? Okay. Oh, and you guys did a lab. Actually, you guys' lab basically was that question we were just looking at, wasn't it? Right? What's the kid's throwing speed? What was the blast speed of the launcher? Okay. This time I'm going to give you guys blast speed. And I want to pick a number that I'm pretty sure is not on anybody's quiz. Okay. I'm going to call the blast like 1,000 meters per second, which is a ridiculously fast speed. Like, actually, it's kind of the maximum I can go before we start hitting like suborbital speeds, right? But I think it's kind of like barely contained. Because at some point you have to consider, well, the Earth is curved, and if you like kind of start throwing around the curvature of the Earth, right? So this kind of runs up against the limit of what we can really do work with. Right? And I'll give you guys the height of the cliff is like 45 meters. Right? 45 meter tall cliff. How? Okay. And then bam, there goes the ball. So first question, the obvious question is like, well, how far? How far the ball go? Like downrange, like from the base of the cliff. What is X? Okay. Oh, yeah, 3,000 meters. Right? How'd you know it's 3,000 meters? Boom, boom, and boom. 1 and 2. Right? You see that? Right? Takes 3 seconds to fall 45 meters. There's your h equals 1/2 gt squared. That's the college equation. And once you know that it takes 3 seconds, it's going across 1,000 meters per second. Apply those two together, boom, boom, 3,000 meters, boom, done. That's it. That's the whole thing. Right? Oh, let me go ahead and write that out, because probably want to write some of your notes, right? If you didn't get that fast. Right? So I'm going to start with vertical information. Okay? Remember, we got 2 dimensions that we're juggling. There's something going on vertical. In this case, it's going to constrain the amount of time the ball's in the air. There's something going on horizontal, which is like the main in question, right? But they involve each other, the 2 dimensions. In this case, vertical is going to constrain how much time is in the air for, right? What's the height of this cliff, and how fast is gravity pulling down? Okay? So that's some version of h equals 1/2 gt squared, right? Just like that. Okay. Now that is a simplified version of this first kinematic expression. Okay? X, it could be some general displacement. In this case, I'm calling it h for vertical displacement, right? H like a cliff height. Okay? Hey, why is this 0? Why is this 0? Isn't it blasting really fast from the cannon? Why call initial velocity 0? Initial velocity in what direction? Vertical, right? Okay. Guys, when that cannonball is being blasted extremely fast horizontally, how fast is it leaving the cannon in the vertical direction? 0 meters per second. It's not moving up or down at all. Right? Now, like 1 second later, now gravity's pulling it down. But right when it's leaving the cannon barrel, okay, this is v naught in the y direction. You guys get that? Right? V naught in the y direction. That's why, right, not moving up or down leaving the cannon barrel. That's why it goes to 0. Now I got the simplified like college equation. I guess that. Okay. Or if you like this, if you blast a ball horizontally and you drop a ball at the same time, who reaches the ground first? Same time, right? So you can think of it that way. You think, well, if I just drop the ball, right? Anyway, it's going to simplify down to this. Okay? We're solving for how much time, okay? Which is not the ultimate question, but it's going to help us figure out the ultimate question of how far does it go. Okay? Now, here's where you guys got a couple of options. You could just plug in numbers at this point, or you could solve in terms of variables. You guys get that, right? I can plug in 45 meters here and 10 meters per second here. Okay? And I can solve for t, and you'd eventually get 3 seconds. Okay? I'm going to do it in terms of variables. Okay? Stretch your guys' imagination a little bit. Could I cross multiply the 2 and divide it down the g? So I get t squared is 2h on g, and then t would just be the square root of 2h on g. Right? Now that's in terms of variables. I haven't actually plugged any numbers in yet. Okay? But that should look familiar from a couple of places. One, the last lab you guys did for years for launch it, basically the setup. Okay? You could calculate the time to fall that way, right? That was involved in your lab. So actually, your lab was like the backwards version of this, right? You guys measured where it land, you back calculated what was that blast speed. I'm giving you the blast speed and ask you guys how far does it go, but you still have to go through time. Right? The other place you can solve this, hey, you guys remember you partnered up, you were like dropping rollers and your partners were catching them? Right? You said, how far did the roller fall? What was my reaction time? That's the other place you saw this. You remember that? Let's plug in some numbers. Let's get the time of fall is square root of 2 times 45 meters divided by 10 meters per second squared. Guys, what's 45 times 2? Time out here. Wait. All right. Let's scratch it. 45 times 2 is 90. What's 90 divided by 10? Square root of 9 is 3 seconds. There you go. Okay. So maybe you remembered that it takes 3 seconds to fall 45 meters, right? If you want to see it written out, that's the longer proof. Let me find yeah. Guys, remember this right here? Guys, remember this right here? That's what we just did, right? All right. Now we got that. Now we're going to switch over to horizontal. Let's look at horizontal. Okay. And then the horizontal direction for projectiles, there's really only kind of one equation you can never apply, which is what? X equals bx times t, right? There's no acceleration in the horizontal direction. Gravity is not pulling horizontally. Right? Gravity pulls vertically, but not horizontally. Right? we've been ignoring air drag. We'll continue to ignore air drag. Okay? That's the only thing you can use. Right? We're asking, how far does it go? Bam, that's that guy right there. Okay? We know, ooh, guys, how fast across is it going? 1,000 meters per second. There's 1,000 meters per second right there. For how much time? Right here, 3 seconds, which we got from the vertical constraints. Okay. Put 2 and 2 together. 3,000 meters. 3,000 meters. Okay. Guys got that? Okay. Follow-up question. Hey, I wonder how fast this cannonball is crash landing, and also what angle is it coming in? So maybe I can say what is the crash velocity? Because that's the 2 parts of velocity, right? How fast and what angle, what direction? Okay. So let's look at the point of crash right down here. It's pow right here. I'm gonna blow that up. And we'll do some math right at that point. So here comes the cannonball. Ooh, notice I drew kind of like the tail end of a parabola, right? I see tail end of a parabola, okay? But right at the moment of crash, it's coming in like this angle right here. I'm gonna call it V crash. I see V crash, something like that. Okay. Here's the actual path that comes on. But right at the moment of impact, it's coming in like that angle right there. Is that right? Okay. Now, to make sense of this, I need to break that crash velocity into what? Starts with the C. Components. You guys remember components? Ah, you guys remember all this trigonometry stuff? Trigonometry? It's back. Trigonometry. Okay. Because if we've got something coming on some angle, the only way I can make sense of that is to know, well, how fast is it coming across? That's V sub x. And how fast in the vertical direction? That's V final in the y direction. Okay. Remember, the y direction gets these 2 subscripts because it's always changing. Right? It's just V final in the y direction. But the crash should be in the y direction, the vertical direction. V sub x is just V sub x. That's the same all the way across. Okay? In fact, I can just put in a number right now for that. You guys remember what V sub x was? Like 1,000 meters per second. Blast speed from the cannon, and the cannon was aimed horizontally, so that just never changes. Okay. Now, V in the y direction. So here's where we need to look back here. Right? So there's basically 2 ways you can get the vertical component of velocity, right, as it's crash landing. Who knows what that value is? Who knows? How fast is it coming strictly down? Yeah, right at the end. 30 meters per second. All right. How'd you know 30 meters per second? Yeah, 10 meters per second for 3 seconds. Boom, boom. Right. So you're thinking of you kind of walk through this one right here, right? In the y direction, it initially wasn't going up or down, so that just zeroes out. So it's picking up 10 meters per second in the y direction. Do that for 3 seconds. 10 times 3 is 30. Right? Could you have also, if you like, played off the height of the cliff, said, well, after falling for 45 meters, maybe plugged into this third kinematic expression. If I put 45 meters here, 10 meters per second squared here, this still starts from 0, right? I could have gotten it that way too, right? Okay. Let's see if those both work out. They should both give you the same thing. Okay. So you could either say Vf in the y direction equals V naught in the y direction, which is 0, plus GT, right? Which is 10 meters per second squared for 3 seconds, which is 30 meters per second. So yeah, this would have to be 30 meters per second. Okay. Or if you liked, the other way you could have done it, get Vf in the y direction squared equals V naught in the y direction squared, which is 0 in this case, plus 2ax. Maybe I'll call it 2gh, 2gy, 2ax, some version of that, right? Okay. So that's this third kinematic expression right here. Okay. So 2 times 10 times 45. Guys, what's 45 times 2? 90 times 10, 900. Square root. The f in the y direction is 30 meters per second. Okay, so it's the same thing, right? It's different. Still this row right here, right? Whether you consider spin falling for 3 seconds at 10 meters per second squared, to get 30 meters per second, or it fell 45 meters. Either way, it's just this row kind of overkill. There's different ways to get to this number, right? Okay. All right, so now we know how fast it's going across, bam, how fast it's come down, bam. Let's put it all together. Can you guys do what am I about to write? Right, square root. Pick up Pythagorean theorem. Pythagorean. 1,000 squared plus 30 squared. The square root of all that. Maybe meters per second for the unit. Okay. Check this out. Okay. Now 1,000 is so big compared to 30. I bet it's not going to change it very much. But let's see. 1,000 squared plus 30 squared square root. Okay. Yeah, it's like 1,000.4 meters per second. Okay. So it picked up a little bit of speed falling, but not very much, right? In fact, that makes me think that maybe this is a pretty big angle, right? Like my picture is probably not to scale at all, right? I'm gonna guess this angle is getting pretty close to 90 degrees, right? Like this is a real shallow parabola right here, maybe like 88 degrees or something ridiculous, right? How could you know for sure? How could you calculate what is that angle theta right there? Theta equals what? Inverse tan, opposite over adjacent. Do something like that. Okay. What is inverse tan? 1,030. Okay. Looking like 88.28 degrees. I'll call it 88 degrees from the vertical. Yeah, so that's a real like shallow parabola. Okay. Okay, you guys got that? Okay, there we go. All right, the other example I want to do with you guys, the other projectile example, the other main category we can do is let's put a cannon right on the ground on a big flat plane and fire it at some angle. Okay. That's not the same cannon, same blast speed, the whole deal. I'm going to aim it up at a 53-degree angle, 53 degrees from the horizontal. Okay. So it's going to blast out that way. Pulse. V blast. Okay. Same cannon as before. Let's go 1,000 meters per second. 1,000 meters per second. Bam! At 53 degrees above the horizontal. Okay. Going to land somewhere over there. Right? I could ask you a few questions about that. Maybe the most classic question could be, well, how far out does it go? Let's call that x. How far x? Okay. Again, you need to juggle two different dimensions. The shallower the angle, like if this is closer to 0 degrees, it's going faster across the field. The steeper the angle, the more time it's in the air for. Right? And both those things have something to do with how far it ultimately goes. Right? So let's start with the vertical information because I want to know the time constraint. I should have asked you guys what's going to constrain the time. You guys would have said vertical, right? Because it has something to do with how fast is it initially going up and how hard is gravity pulling down. But you can't make sense of that until you break this blast velocity into what? Components? What you're going to do? Break this into components. I see a nice right triangle right there. Right? Okay. So 1,000 meters per second at 53 degrees above the horizontal. Okay. V sub x equals what times what? Okay. So something to do with the overall blast speed, 1,000 meters per second. And something to do with this 53-degree angle. What am I going to multiply by? Cosine of 53 degrees, right? Because cosine translates hypotenuse to the adjacent leg. This is adjacent to 53 degrees. That's why you need cosine. Okay? I'm just going to call that a nice round 600 meters per second. Okay. Okay. So it's always going across the field at 600 meters per second. That's going to be constant all the way across, like 600 meters per second. Okay. Now the vertical is a little trickier because it's constantly changing velocity in the vertical direction. I'll call this leg the initial in the y direction. Well, notice it gets two subscripts, right? Yes, it's in the y direction. It's also the initial case. Sometimes you see it the other way, so b, y, not. It'd be not y, but whatever, right? But is that going to be 1,000 meters per second times what? Sine of 53 degrees? Because sine is going to translate from your hypotenuse to the opposite leg. Yeah, this is opposite of 53 degrees. You see that? Okay. I'm just going to round that to nice, even 800 meters per second, which is pretty close to 800 meters per second. Yeah, see, I was picking 3, 4, 5 geometry, right? You see that 53-degree angle right there, or 37 degrees for that matter. Okay, you guys get that set up? Okay. All right, so now we know how fast it was initially going in the vertical direction and how fast it's always going across the field. We know both those things. Okay. So let's break out some vertical equations to figure out the time constraint. Okay. In fact, before I write anything down, I bet some of you guys can just eyeball that and be able to tell me. Right. Now, there's different ways you can finish this problem off, but suppose I want to break this in half. I want to know like how much time does it take to get from here to the maximum height point? Maximum height point. Can anybody just look at that, look at my numbers, and tell me how many seconds it takes to reach the maximum height? How many seconds? How much velocity is it losing in the vertical direction every second? 10 meters per second every second it's losing? Because it's slowing down on the way up, right? Right? At the very top, it's going how fast vertically? 0 meters per second vertically. Right? Now, of course, it's still going across, but it's just not going up or down right at the very top. Okay. Oh, hey, if it started 800 meters per second straight up, and it's losing 10 meters per second every second, how many seconds is that to get to the top? Like 80 seconds? You guys see 80 seconds? Ooh, right. Which, yeah, this is pretty ridiculous blast speed for a cannon, but be like over a minute. Okay. So the equation I can use to back that up is going to be this guy right here, right? Okay. This is not the only way to solve this problem. I'm just taking guys through one path through the forest. Right? Now I do need something with vertical information going on. Right? I'm going to say v final in the y direction is equal to v initial in the y direction minus g times t. Right? Looks like it blasted it upish. Gravity's pulling down. Okay, so that's why I had to subtract, right? And at the very top, what is the vertical velocity at the very top? 0 meters per second. It's not going up or down at the very top. Okay. I know it started at 800 meters per second. It was going straight upwards. I'm losing 10 meters per second. So copy this number. Okay. Now, guys, the way I've set this up, is this the total hang time or is this half the total hang time? It's gotta be, yes, see, it's only gonna be half the story, right? Because I'm only taking it to where the top goes to 0 meters per second. Okay. So I'm gonna put a subscript on this t. I'll call it half. Half the total hang time. All right, so whatever time we get, it's only gonna take us up to here. Okay. Little algebra shuffle, subtract over 800, divide by -10. Yep, time, oops, half the time, I should say, is 80 seconds. 80 seconds it takes to get to the very top. Okay. Therefore, what is the total hang time to get from the cannon all the way back to the plane? What's that going to be? Guys, if it's 80 seconds up, how many seconds back down? Another 80. 160 seconds. You guys think? 160 seconds? Okay, guys, yeah? Okay. All right, so with this setup, with this blast speed at this angle, it's going to take, like a solid, what is it, like over 2.5 minutes, something like that, to get back down to the plane. Okay. Now we can go in for the final question. Let's switch over to horizontal information. Horizontal. Okay. And horizontally, there's only one expression that ever applies. What equals what times what? X equals v sub x times t. Okay. Okay. There's no acceleration in the horizontal direction. Gravity's not pulling horizontally. We've been ignoring air drag. We're going to continue to ignore air drag. It's just going across at constant speed. You can think of it that way. Right? And how fast is it going across? 600 meters per second. That's that number right there. For how much time? About 160 seconds. Right there. Right. Put it all together. 600 meters per second across for 160 seconds. Looks like 96,000 meters. You call it like 96 kilometers. That's a pretty good road trip right there, right? Is that like across the state of Florida, about somewhere thereabouts? Okay. Okay. Yeah, that's probably the maximum blast speed I could pick for a cannon before it starts going to like weird like suborbital type motion. You have to consider, well, okay, the Earth is actually curved, right? Okay. So that would probably be pretty close though. Okay. Okay, you guys good? All right. What about if I ask you, here's what, I need, how much time we got in here? Got till 28. Okay. Okay. Let's do this a different way maybe. What if could I have skipped past like getting half the hang time, just got the full 160-second hang time? Right. What if you go from the plane back to the plane? Right. And maybe I want to think about this in terms of displacement. Right. Here's a different way. Again, this is not the only other way to do it, but this is just a different way to also have done the same thing. Right. Guys, what's the displacement from the plane back to the plane? The vertical displacement. I meant, what's the vertical difference from the plane back to the plane? Zero. You guys see? There's no height change, right? I could break out this first kinematic expression and call this height change, in terms of vertical, call that zero. Okay. And I should get the same results. Let's try that. Let's go. Y equals v naught in the y direction, t minus 1/2 gt squared. Okay. I'm backing up. So suppose either want to confirm my answer or didn't know we're doing this from scratch this way. We'll solve for the time that way. Ooh, now at a glance, this looks like it's going to be quadratic. You guys see like a quadratic it wants to be, quadratic formula? Okay. But that's okay. We're going to get past that because this is equal to 0 meters from beginning to end. 0 meter height difference from the plane back to the plane. Okay. Therefore, I can factor a t out. Let's factor a t out right here. And then divide that t over. 0 divided by t, it just goes away. Okay. Ooh, so we just skirted right around the quadratic formula. Okay, you guys see it? Okay. Right. 0 equals, well, v naught in the y direction was 800 meters per second. Okay. It's right there, 800 meters per second. Minus 1/2, 10 meters per second squared for the full hang time. This is the full hang time right there. Okay. I'll divide everything by 10, I guess, whatever. Okay. Okay. Add over, or subtract over 80, multiply by -2, t hang, full hang time, 80 times 2, that's 160 seconds. Oh, hey, that's the same thing we got before. 160 seconds. We found half the hang time and doubled it and also got 160 seconds. Just a minute. So there you go. There's a different method. Right? There's other ways you could do too. Right? And then it would just finish out the same way. Right? Guys got? How about this? What is the maximum height? What's the maximum height of this thing? Okay. Now, if you want maximum height, guys, maximum height. I could only possibly use two of those three. I can't use which one for maximum height. Which one does not apply to? Do you guys see the middle one has nothing to do with, it doesn't say anything about displacement. Okay. So I definitely can't do that. I could get maximum height using the third one. I could get maximum height using the first one. You guys see that? Okay. Here, I'll just go ahead and use the first one just to pick one around with it. Right. But you could do multiple ways. So I could go H max equals V naught YT minus 1/2 GT squared. I could do something like that. Okay. H max equals, well, V naught in the y direction I know was 800 meters per second. Now this t, what am I plugging in for t? How many seconds? For how many seconds from here to here? 80 or 160? 80, yeah, 80. So this is really half the hang time right there. Yeah, 80 seconds. Minus 1/2 times 10 meters per second squared for 80 seconds again, squared. Don't forget to square that one, right? So this is going to tell me how high does that cannonball go at a maximum. 800 by 80 minus 1/2 by 10 by 80 squared. 32,000 meters, or if you like, 32 kilometers. Woo! That's like above Mount Everest. Crazy cannon. Right? So, yeah, other ways you could also solve it and get the same answer, but there's one way to do it. So in terms of time. Right? Pretty good. All right. So while you guys are finishing putting that in your notes and digesting that, I'm gonna get you guys to your next take-home quiz, which is going to be due on this Friday. This Friday, next take-home quiz. All right. Hey, got everybody? Everybody's got a take-home quiz now. All right. All right. So great. Got last few minutes here. Want to set you guys up with the next stuff that we're doing. So tomorrow, you're going to give guys a spring scales lab. Really, it's going to be like 10 mini labs. And I want you guys to pay real close attention to what you're doing tomorrow, because I'm going to continue to reference that lab for many weeks to come. There's going to be 10 different type of activities we're going to have to do this. I'm going to introduce you guys to these spring scales. Now, these spring scales, you pull on them like with some force, and they'll stretch by some amount. Interesting. Right? And the different colors have different stiffness springs in them. Right? So the blue ones have not a very stiff spring. You put a tiny force, it stretches a lot. It's like nothing. Right? The gold ones is like, oh, I put a huge force on it. It barely stretches it off. Oh, man, it's so much force, it barely stretches. The brown ones are, I think, the most versatile. They're kind of like a medium stiffness. Okay? So like I could pick up some lab weight with this, right? And it'll tell me like how many newtons of force it is. By the way, there's two readings on this each spring scale. On one side it says force in newtons. On the other side it says mass in grams. Now those are totally different concepts, right? The mass in grams really only applies to what mass at the surface of Earth would have resulted in a weight that would give a force that would stretch the spring by such amount. Okay. The newtons, how many newtons? That quantifies like a force. Guys, all a force is just a push or a pull. If I push on something, if I pull on something, I can quantify that in newtons. When you guys are doing your lab tomorrow and you're looking at these spring scales, do you guys want to focus on the grams or on the newtons? How about newtons, right? For force, right? So don't really pay attention to grams. That's okay. I care about the force in newtons. That's what we're using these for, right? Force in newtons, right? Guys go there. Okay. Now, one of the packets the packet I just gave you guys at the beginning of class, it's got Newton's first law of motion, 20 questions, Newton's second law of motion, 20 questions, Newton's third law of motion, 20 questions. I'd like to do all the cahoots with you guys in the next few weeks, but we'll see how that plays out. But on the back, ooh, hey, look, it's some of the posters that here. You guys see I got new posters rotated in. You guys see new posters hanging here? Right. So I picked 6 that I thought would probably be most useful and printed because 6 will fit on a page. There you go. Hey, look at the first one. Hooke's law. Hooke's law tells you how much a spring will stretch if you put a force on it. And look, that's a direct relationship. You guys see F equals KX. And so what are we looking at here? So F represents a force that you can quantify in newtons. X represents how much it either stretches or compresses from an unstretched position. Okay? Now these spring scales are only going to stretch, but you might see a compression question somewhere, right? It's the same idea. Okay. So if it's unstretched or uncompressed, maybe okay, the spring is some original length. If I push on it, it's going to compress. If I pull on it, it's going to stretch, maybe by some amount X. Okay? That amount X that I stretch, okay, is directly proportional to the force that you put on it. Right? If you put like 3 times the force, you'll get 3 times the stretch distance. You guys see that? Okay. Now this K is what's called the spring constant. that has something to do with how stiff is the spring. Oh, this blue one has a really small spring constant. A tiny force will stretch it a lot. This gold one is like the opposite. This one has a huge spring constant, but a huge force. It barely moves at all, right? And the brown ones are kind of, again, I think like most versatile. They're probably the most useful spring scale tomorrow, right? Okay. Kind of in the middle. Okay. Now, some textbooks throw a negative sign here. They say F equals negative kx. The idea being that F would represent the restoring force, so that if you stretch it out, say to the right, the spring is actually pulling back to the left. That's like where the negative sign would come from if there's a negative sign here. More often than not, I don't throw that in there, but okay. That's kind of how the spring scales work. Right? You guys get that? So you guys can measure forces tomorrow? You guys can measure forces? Right? All right. All right. So bell about to ring. I think I got to wrap up right there. But here's the tile card. All right. You guys got any last questions for today? All right. So let's call it a wrap right there.